Welcome to this problem walkthrough. Today, we'll explore LeetCode problem number 1822, sign of the product of an array. This problem challenges us to determine the sign of the product of all elements in a given array. We'll break it down step by step, examine the best approaches, and discuss its complexity. Let's dive in. In this problem, you are given an integer array called nums. The task is to determine the sign of the product of all the elements in this array without actually calculating the product itself. The result you return must be one of three values. If the product is positive, you return 1, if the product is negative, you return -1, and if the product is 0, you return 0. The input constraints for nums ensure that the array will have at least one element and no more than 1,000 elements. Each element in the array will be an integer between -100 and 100, inclusive. Your output will always be a single integer representing the sign of the product. Let's look at an example to understand this better. Suppose the input array is nums equals -1, -2, -3, -4, 3, 2, 1. The product of all the elements in this array is calculated as -1 asterisk, -2 asterisk, -3 asterisk, -4 asterisk 3 asterisk 2 asterisk 1, which equals 144. Since the product is positive, the function returns 1. This example demonstrates how the sign of the product determines the output, regardless of the actual magnitude of the product. Now, consider another example where the input array is nums equals 1, 5, 0, 2, -3. Here, the product of the numbers is 1 asterisk 5 asterisk 0 asterisk 2 asterisk, -3, which equals 0. Notice that the presence of a 0 in the array makes the entire product 0, no matter what the other numbers are. As a result, the function returns 0 because the product is 0. Finally, let's look at the array nums equals -1, 1, -1, 1, -1. The product of these numbers is -1 asterisk 1 asterisk, -1 asterisk 1 asterisk, -1, which equals -1. Since the product is negative, the function returns -1. To summarize, if the array contains a 0, the function should return 0 immediately. For arrays without 0, the sign of the product depends on the count of negative numbers. An even count results in a positive product, while an odd count results in a negative product. These constraints and edge cases help guide an efficient solution to the problem. To solve problem number 1822, the goal is to determine the sign of the product of all elements in the array nums. While it might seem natural to compute the product directly, this approach has some drawbacks. Let's explore the brute force method first. Here, we initialize a variable product as 1 and multiply it by each element in the array. At the end, we would return 1, -1, or 0 based on the sign of the product. However, there are significant issues with this approach. If the array contains a 0, the product will always be 0, but we would still perform all the multiplications unnecessarily. Additionally, if the product grows very large, there's a risk of integer overflow. Finally, this method is inefficient because we don't actually need the full product, just its sign. Although the time complexity is O(n), the brute force method is not the ideal solution for this problem. Instead of calculating the full product, we can use a more efficient and stable approach by focusing on the sign of the product. This is our chosen solution, called the optimized sign counting approach. Here's the key insight: there are only three factors that determine the result. If the array contains a 0, the product is 0. If the number of negative elements is odd, the product is negative. If it's even, the product is positive. To implement this, we initialize a counter -_count to 0. As we traverse the array, we return 0 immediately if we encounter a 0. For negative elements, we increment the counter. Finally, we check if -_count is even or odd and return 1 or -1 accordingly. This approach avoids the risks of overflow entirely, as we're not performing multiplication. It's also more efficient since we can stop early if a 0 is found. With a time complexity of O(n) and constant space usage, this method is both simple and optimal. Another alternative is to use a Boolean flag instead of counting negatives. In this method, we initialize a flag as -negative as false. As we iterate through the array, encountering a 0 still allows for early termination with a return value of 0. For every negative element, we toggle the value of is_negative. At the end, the flag's value determines the result. If is_negative is false, the product is positive, so we return 1. Otherwise, we return -1. While this approach is similar in efficiency to the optimized sign counting method, it has some drawbacks. Using a Boolean flag can be less intuitive than a counter, especially when debugging or explaining the logic. The process of toggling the flag might also make the solution harder to follow, making this method less favorable compared to counting negatives. The optimized sign counting approach is the best solution due to its simplicity, clarity, and efficiency. The main insight is that we don't need the actual product, only the number of negative elements and the presence of zero matter. This eliminates unnecessary computations and avoids overflow risks. Early termination when encountering a zero adds further efficiency. The brute force approach, while straightforward, is computationally expensive and prone to overflow, making it unsuitable for large input arrays. Compared to the Boolean flag method, the sign counting approach is more intuitive and easier to debug, as a counter is clearer than toggling a flag. In terms of trade-offs, this method strikes the right balance between efficiency, readability, and robustness, making it the ideal choice for solving this problem. The task in this problem is to determine the sign of the product of all elements in an array without actually calculating the product. This means we focus entirely on the sign positive, negative, or 0. The output should be 1 if the product is positive, -1 if it's negative, and 0 if the product is 0. To solve this, we rely on the properties of multiplication signs. For example, if any number in the array is 0, the product is automatically 0. Additionally, when dealing with negative numbers, the product of an even number of negatives is positive, while the product of an odd number of negatives is negative. Instead of directly calculating the product, risking inefficiency and potential overflow, we can simplify the process by counting how many negative numbers exist and checking if the array contains any zeros. With this understanding, the algorithm begins by initializing a variable to track the count of negative numbers and then traverses the array step by step. The algorithm proceeds by first addressing the presence of zeros. If the current element in the array is 0, we immediately return 0 since any product involving 0 will always result in 0. This ensures an early exit and saves unnecessary computation. Next, as we iterate through the array, we count the negative numbers. For every negative element encountered, we increment the negative_count variable. Once the traversal is complete, we determine the sign of the product based on the value of negative_count. If the count is even, the product is positive, so we return 1. If the count is odd, the product is negative, and we return -1. This approach not only avoids directly calculating the product but also ensures we handle large or small numbers without risking overflow. Additionally, the early exit for zeros and the simplicity of the logic contribute to making the algorithm both efficient and robust, with a runtime of O(n), since it requires only a single pass through the array. To implement this algorithm, we rely on minimal data structures. The input array, nums, is traversed directly, and we use a single integer variable, negative_count, to keep track of the number of negative elements. This ensures the space complexity remains constant at O(1). The code implementation reflects this simplicity. We start by initializing negative_count to 0. As we iterate through the array, we check each element. If the element is 0, we immediately return 0. If it is negative, we increment the negative_count. After completing the loop, we determine the result by checking whether negative_count is even or odd. An even count results in 1, while an odd count results in -1. This concise and efficient solution is robust and handles the majority of edge cases effectively, including arrays with zeros, all positive numbers, or all negative numbers. The algorithm is designed to handle various edge cases seamlessly. For instance, if the array contains a 0, the function terminates early and returns 0. If all numbers are positive, the result is 1 since there are no negative elements. For arrays with only negative numbers, the result depends on whether the count of negatives is odd or even. In cases with mixed positive and negative numbers, the sign is determined purely by the count of negatives. Even an empty array is not a concern due to problem constraints that guarantee valid input. The algorithm's efficiency is evident in its complexity analysis. It runs in O(n) time since it requires only a single traversal of the array. The space complexity is O(1), as it uses only a constant amount of additional space. Key optimizations like early termination when encountering a zero and the avoidance of direct product calculation contribute to both clarity and performance, making the algorithm highly effective for this problem. The solution to LeetCode problem 1822, sign of the product of an array, is implemented in Python. The problem asks us to compute the sign of the product of all elements in the input array nums without directly calculating the product. The solution starts by initializing a variable sign to 1. This variable represents the cumulative sign of the product as we iterate through the array. The key insight here is that multiplying by a negative number flips the sign from positive to negative or vice versa, while multiplying by a positive number leaves the sign unchanged. The program then iterates through each number in the array. If it encounters a 0, it immediately returns 0 because the entire product becomes 0. Otherwise, if the number is negative, the sign variable is flipped by multiplying it by -1. Positive numbers leave the sign variable unchanged. By the end of the loop, the sign variable reflects the overall sign of the product of all elements in the array. The function then returns this value, which will be either 1, positive product, or -1, negative product. This approach is efficient, as it processes the array in O(n) time, where n is the length of the array. It avoids directly calculating the product, which prevents potential overflow issues. Additionally, it handles edge cases such as arrays containing zeros or entirely positive or negative numbers effectively. This is the Java implementation of LeetCode problem number 1822, sign of the product of an array. The logic mirrors the Python implementation. The array sign method iterates through the array, checks for zeros, and flips the sign for negative numbers. Key differences include the use of Java's enhanced for loop and type declarations for variables. The method directly returns the sign of the product without calculating the product explicitly, ensuring efficiency. To solve this problem, we start by initializing a variable sign to 1. This variable will help us keep track of the overall sign of the product as we iterate through the array. Now, looking at the first number in the array, which is -1, we see that it is less than 0. Whenever we encounter a negative number, we flip the sign by multiplying sign by -1. This changes the current value of sign to -1. Moving to the second number, -2, we notice it is also less than 0. Again, we flip the sign by multiplying by -1, which brings sign back to 1. For the third number, -3, we repeat the same process. Since it is negative, the sign flips once more, and sign becomes -1 again. Next, we continue with the fourth number in the array, which is -4. Because -4 is less than 0, the sign flips again by multiplying sign by -1, resulting in a value of 1/4 sign. Finally, we evaluate the last number, 3. Since 3 is greater than 0, the sign remains unchanged. At the end of the iteration, the value of sign is 1, which tells us the product of all numbers in the array is positive. Therefore, the function returns 1. Now, let's consider a different example. If the input array is 0, 1, -1, we start with sign initialized to 1. The first number is 0. Since 0 immediately makes any product 0, there's no need to continue further. The function immediately returns 0 as the result. In the third example, the input array is 1, 2, 3, -1. Here, we start by initializing sign to 1. The first number in the array is 1, which is greater than 0, so the sign remains unchanged, and sign stays as 1. Moving to the second number, 2, we see it is also greater than 0. Again, the sign remains unchanged, and sign is still 1. For the third number, 3, the same logic applies. Since 3 is greater than 0, the value of sign does not change and remains 1. Finally, we evaluate the last number in the array, which is -1. Since -1 is less than 0, we flip the sign by multiplying sign by -1. This changes the value of sign to -1. At this point, we've gone through all the numbers in the array, and the final value of sign is -1. This indicates that the product of all numbers in the array is negative. Therefore, the function returns -1 as the result. The time complexity of this solution is O(n), where n is the number of elements in the input array, nums. This is because the function processes the array in a single loop, iterating over each element exactly once. During each iteration, it performs a constant time operation, such as checking if the current number is 0 or negative. For negative numbers, it also adjusts the sign variable, which is another constant time operation. Since these operations do not depend on the size of the array, they add up to O(1) for each element. Multiplying this by the total number of elements, we get an overall time complexity of O(n). In the best case, if the array contains a 0, the function exits early after processing up to the first 0, resulting in OK, where k is the index of the 0. On average, the function processes all elements, giving us O(n). In the worst case, when no zeros are present, the function must traverse the entire array, which is also O(n). This makes the solution efficient across different scenarios. Next, let's discuss the space complexity. The solution uses only a single integer variable, sign, to keep track of the cumulative sign of the product. It does not require any additional data structures or modify the input array. This means the memory usage remains constant, regardless of the array's size. As a result, the space complexity is O(1). This efficient use of memory is a key advantage of the solution, making it suitable for handling large input arrays without any additional overhead. Now, let's compare this approach with the brute force method. A naive solution would calculate the product of all elements in the array and then determine its sign. While the time complexity of this approach is also O(n), as it still requires traversing the array, the multiplication itself can be problematic. For large arrays, there's a risk of integer overflow in languages with fixed-width integers, even though Python manages arbitrary precision integers. In terms of space, the brute force method may not require additional memory, but the intermediate product value could still consume significant memory resources in some cases. On the other hand, the optimized approach avoids these issues entirely. By focusing directly on counting negative numbers and detecting zeros, it eliminates the need for actual multiplication, preventing overflow risks. It retains an O(n) time complexity while being superior in space efficiency with O(1) memory usage. This makes the optimized solution both faster and safer in practice. Finally, let's solidify the analysis with a mathematical proof of the big O complexity. Suppose the input array has n elements. The loop runs once for each element, resulting in exactly n iterations. Within each iteration, the operations performed are all constant time, or O(1). Multiplying the O(n) iterations by these O(1) operations gives a total time complexity of O(n). For space complexity, the algorithm uses only a single variable, sign, and no additional memory, which keeps the space complexity at O(1). In conclusion, this solution is highly optimized, achieving both time efficiency with O(n) and memory efficiency with O(1), making it a robust approach for determining the sign of the product of an array. When solving this problem, there are a few common mistakes that can lead to incorrect results. One major error is directly multiplying all the elements in the array to compute the product. This approach can cause integer overflow, especially when the array contains very large numbers. Even if you're just trying to determine the sign, performing the full calculation is unnecessary and inefficient. Another mistake is ignoring zeros in the array. Remember, if the array contains even one zero, the product is 0, and failing to account for this can lead to an incorrect output. Additionally, mishandling negative numbers is another frequent issue. You need to carefully count how many negative numbers are in the array because an odd count results in a negative product, while an even count keeps the product positive. Miscounting or overlooking this can easily lead to errors in the result. Another common pitfall is overcomplicating the problem. Some might use extra data structures like lists or perform unnecessary calculations to determine the product's sign. This adds unneeded complexity, especially since the problem can be solved in linear time with a single traversal in constant space. It's also important not to overlook edge cases. For instance, what happens if the array is empty or contains only one element? An empty array might require special handling based on the problem's constraints, though in this case, it's invalid. Arrays with just one element should also be carefully handled, as the solution in this scenario is simply the sign of that single number. When discussing this problem in an interview, there are several key insights you can highlight. First, focus on pattern recognition. The sign of the product depends solely on the count of negative numbers and the presence of 0 in the array, not the actual values themselves. Recognizing this simplifies the problem significantly. It's also important to communicate your approach with clarity and simplicity. Explain why directly calculating the product is wasteful and how you can achieve the result more efficiently. Additionally, proactively addressing edge cases like arrays with only positive numbers, only negative numbers, zeros, or a mix demonstrates thoroughness. Finally, emphasize the efficiency of the optimal solution, which achieves O(n) time complexity with O(1) space, and contrast it with the brute force approach. If time allows, you can also discuss trade-offs between different methods to show deeper understanding. There are also related problems that share similar themes or concepts. For example, LeetCode 628, maximum product of three numbers, involves working with the product of array elements and requires careful edge case handling. Another example is LeetCode 1186, maximum subarray sum with one deletion, which also emphasizes the importance of edge case handling and efficient array traversal. In terms of alternative approaches, there are a few worth considering. The brute force approach involves directly multiplying all the elements in the array, but while it's simple, it's prone to overflow and inefficient for large arrays. A more optimal solution is to use a counter for negatives while checking for 0 in a single traversal. This method is both efficient and avoids numerical instability. Another possible approach is sorting the array to analyze the signs, but this adds unnecessary complexity with O(n) log n time and is generally overkill for this problem. Thank you for following along. To summarize, we explored the efficient solution for determining the sign of the product of an array without explicitly calculating the product. This problem highlights the importance of logical reasoning and optimized traversal. If you found this helpful, don't forget to like, share, and subscribe for more problem-solving content. See you in the next one. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!